Before we start this video, it's imperative that you know what the principle of superposition means, that you know what path difference means, that you know what coherence is and what makes two waves coherent. And perhaps most importantly, that you know how to use path difference and phase difference. If you're not sure, go back, review the answers on interference and superposition. So if we take our beam of light and we shine it through a narrow slit from the starter, that light would probably diffract. And what we would see if we put, say, a screen here is some kind of smudgy spot. It would be brightest in the middle and then it would kind of fade out towards the edge. So when you diffract light, you wouldn't see what was going on here, but when you put a piece of paper in front of it or you put a screen in front of it, you would see a smudgy red dot. The question that's really interesting is, what if I took my beam of light and shone it through two of those slits that were very close together? And you get this area here where they will superpose. The two refracted rays will superpose in that space there. This is really interesting when you ask, what happens when I put my screen in front of it? Now if I could show you this in real life, we could do this with, I don't know, like a laser and some little very closely spaced slits, and we would see that in the center of the screen there is a bright spot. But as we move away, it goes dark again, and then there's another smaller, brighter spot, and then another, etc. And it's a mirror image on the other side. So weirdly, when we shine our light through this double slit, we get this pattern of what we call fringes. So this will be a bright fringe, dark fringe, bright fringe, dark fringe, etc. And the reason for this unexpected effect is the superposition that's going on, the adding up of the amplitudes of these waves in this region here. So let's take a look at what's in the book. In the book, next to the fill in the blanks, you have this diagram and it crops up 4 times in a row. I'm going to draw it once in big. There's a double slit, there's a screen over here. On that screen is the pattern that we see with the central bright fringe, another one up here, another one up here, etc. It doesn't have anything on it at the moment, and I actually think it's really good that's not come up in the answers, because it means that I can explain what you have to draw on it here. In the first part of the task, it says light coming from the top slit and bottom slit reach this central maximum here. I would like you to draw that on. If I draw light leaving this slit and light leaving this slit, they will reach this central point here. The difference in distance between here and here is the same as the distance between here and here. The path difference is 0, and so the waves arrive in phase. The path difference is 0, the phase difference is 0. This is a constructive interference. So the reason for that bright central fringe, and it's brighter than everything else, is because in the centre there you're getting pure constructive interference between those two waves. Let's have a look at the next bit up. I'll do it in blue. If I take a wave from here, so they're coming from the same points of the slits, but instead I'm going to go to the dark fringe. Now hopefully you can see the wave from the bottom has kind of travelled along a hypotenuse of a triangle. This wave here has travelled in a straight line. So the wave coming from the bottom has travelled further than the wave at the top. Why is that important? Well, here we see nothing. There is destructive interference. This tells us that the phase difference is 180 degrees, and therefore the path difference must be exactly a half of a wavelength. It's the first time where we get this phase difference of 180 degrees. It must have a path difference of a half of a wavelength at this point. We could continue this for all of the spots. What we would end up with, and I'll use the bottom of my diagram to demonstrate this trend, this is really, really important. Where you get a bright fringe with constructive interference, the phase difference is 0, they're both arriving in phase, constructively interfering, because the difference in path between this top slit and this bottom slit, getting to that point, must be a multiple of the wavelength, and that is a whole number multiple of the wavelength. For the dark areas, it's the converse, so these are destructive. Here the phase difference is always 180 degrees, the path difference is always a half wavelength, where n is odd. It must be odd because otherwise 2 divided by 2 would just give you the wavelength here. It has to be 1, 3, 5, 7, 9. I hope that makes sense and it helps you understand what those points in the book are making. I think it says it best in the book. Take time to just process what's written down there, but do add these little lines as described onto your diagram. When we look at the setup for Young's double slits, as per this diagram in the booklet, we know the difference in distance between the slits, we know the wavelength of our light, and we know how far away the screen is. The longest distance in this experiment by far is the distance between the slits and the screen. This is going to be centimetres, metres, it's going to be a big distance, so it's a capital D. Remember that one. That's on the bottom of this equation. X is the separation of fringes, so the distance between the centre of one bright fringe and the next bright fringe down. They are equally spaced in a Young's double slits experiment. A is the distance between slits. Remember that that has to be quite small. We're talking 10 to the minus 6, 10 to the minus 9 of a metre. The wavelength, as you know, is probably, for light, 10 to the minus 7 metres. There are two slight variations on the Young's double slit experiment. If I use white light, I get a whole spectrum, a really cool rainbow pattern like this. Really interesting, and that's simply because for the different wavelength you get a different fringe spacing, so the Young's double slit actually separates that white light out into different wavelengths. Obviously the central fringe will occur in the same place, so you get a white central fringe surrounded by a kind of rainbow pattern of outer fringes. If I use more slits, more than 2, sometimes we use an entire grid of slits, and that's called a diffraction grating. The more spread out the fringes are, and the clearer they are, the better defined. And you can see what I mean by that in that image. You can clearly see where each individual fringe is, and they are much further apart than they were before. Those two variations are just things to know. We do revisit this effect where we use a thing called a diffraction grating in booklet 5.10, looking at stars. So after watching this video, reading through the notes and doing some practice, you should be able to close your book and explain these things. Why do bright and dark fringes form? What does A mean? X, D, obviously what does lambda mean? And you should be able to think about how this equation would affect the outcome. So if I were to change the slit screen distance, if I was going to move the screen away, or if I was going to change the colour of light,